So in this video we will I'll teach you how to use Kirchoff's second law to solve various problems. So let me write the title: Kirchoff's second law. Now you need to understand that you can understand it as a law of conservation of energy. Okay, so let me write that down. It's a law of conservation of energy applied to electric circuits. So let's see how it is so. So let me draw a simple circuit first. We'll start with we need to have a resistor. We'll have two resistors. Then we have a cell. Then we close the circuit. Okay, don't worry about the key. That's not important for our discussion. So let's call this resistance R1. Let's call this resistor R2. This is a cell of EMF eta. Okay. Now for this EMF eta, let us say there is a current in the circuit of value I. It will come. Oh, I put the wrong direction. Wait a second. So current always comes out of the positive terminal of the cell, conventional current. So let us say this is the current I. So now if I have to apply Kirchoff's second law to this circuit, it can be applied to any circuit to find out what is the current in each branch of the circuit, to find out what is the potential drop across any resistor. That's the use of Kirchoff's second law. Okay. So here I will demonstrate all the rules of how to apply Kirchoff's second law. So it says that the sum of the changes in electric potential. So delta is change and V is potential. So sum of the changes in electric potential across an entire loop, okay, is 0. If you want to understand why it is so, how it is so, I can explain it by using an analogy. So the analogy we will use gravitational analogy. So let us say you have a box of mass m on the floor at position A. You lift it by a height h to a position B, and then you move it sideways to a position C. This is position B, and then you bring it down by the same height h to position D. And then you bring it back to starting position A. So now if you calculate what is the change in potential, in this case gravitational potential, in moving this object from A to B to C to D and back to A, that is, it moved through a closed loop, you will find that the change in total potential is 0. How? Let us see. Gravitational potential would be defined as gravitational potential energy by unit mass. So gravitational potential is gravitational potential energy by unit mass. So U by M. Right? Now potential energy at A, potential energy, gravitational potential energy is mgh. H is 0 here. So it is 0. So 0 by M is 0. So here it is 0 at A. Potential at A is 0. Gravitational potential at B is mgh by M. So mgh by M. So M will cancel out, you get gh. Gravitational potential at C is again mgh by M. So it's again gh. And gravitational potential at D is 0. Now let us see what is the change in potential from A to B, B to C, C to D and D to A. So A to B is, let us call this delta 1, change in potential first part, it is final minus initial. So GH minus 0 is GH. Then delta 2 is GH minus GH. So it is 0. Delta 3 is 0 minus GH. 0 minus GH. So it is minus GH. And delta 4 is 0 minus 0. Finally it is 0 here. Initially also it is 0 here. 0 minus 0 is 0. So what is the total change in potential from A to B to C to D? It's GH plus 0 minus GH plus 0. I am recording. So it will be 0. GH minus GH.
Why so?
What do you mean why? From here to here the change in potential is GH.
GH plus 0.
GH plus 0 is GH minus GH. That GH and this GH cancel out. So it's 0. Plus 0 is 0. So total change in potential is 0. I didn't write the individual zeros. It's a waste of time. So this is an example in gravitation. So when an object is moved in the presence of a gravitational force, this happens. Similarly, in an electric circuit, the charge is moved in the presence of an electric force. So again the same thing will happen. So electric potential energy will be conserved. So see, what is happening is the potential at A is fixed value, 0. Wherever you go, again if you come back to the same place, your final potential is same only. Is it not? Yeah. So what is the change in potential if you go roam all over the place and come back to the same place? 0. Because the potential at a given point is fixed. Wherever you go, again you come back to the same place. It's like displacement. It's like displacement is 0. You go wherever you go, and if you come back to starting position, your total displacement becomes 0.
So if you start from this point also, it will become 0.
If you start from B and if you come back to B, the change in potential will be 0. If you start from B and come to A, change in potential will not be 0 because you did not come back to starting position. You have to, in a circuit, you have to follow a closed loop and come back to the starting position. Then the total change in potential is 0. Clear? So now we need to apply this in the circuit. So now you see here, if a cell is there, the negative terminal is lower potential. We will call it VL, V lower potential. Positive terminal is higher potential, VH. Right? So now imagine that you are the positive charge and you are going through a circuit. So you will just see how the potential changes for you. You are an imaginary positive charge. So you can go in any direction you want, clockwise or anti-clockwise. So let's go clockwise. Okay? So let's go like this. So we'll start from here, from this point, and we'll come back to this point. So now you see here, this is higher potential, this is lower potential. So when you go across a cell from positive to negative, your potential is becoming more or less? Less. So the change is positive or negative?
Change is negative.
Yes. So final minus initial is negative. So the difference in potential between the cells of between the terminals of a cell is EMF eta. So the change when you went across the cell is minus eta. Then here there is no resistance, so there is no change in potential. Now you reach this end. Now look here, the current direction is like this. Now current will always flow from higher potential to lower potential through a resistor. Now you are going against the direction of current. So this point is higher potential or lower potential? You are going against the direction of current. Now current flows from here to here. This is higher potential or lower potential?
Higher.
Yes, because current will flow only from higher to lower potential. This is lower potential. Agreed? So now when you go from here to here, you are actually going from lower to higher potential as an imaginary positive charge. So your change in potential would be positive or negative?
Positive.
Positive. So that would be VH minus VL in this region, and the difference in potential across a resistor is given by Ohm's law. V is equal to IR. So the current here is I, resistance is R1. So the potential difference magnitude is IR1, and in this case it is positive because you are going against the direction of current. Imagine you are going upstream. Imagine the current is like a river River will flow from greater height to lower height. So whenever you go against the flow of water, you are going up. So you are reaching higher potential, the higher gravitational potential. Like that, when you go against the direction of electric current, you are going up. Your electric potential is increasing. So it will be plus. It will be plus IR1. Clear? And then here also plus IR2. Because I told you the change in potential across R1 is positive. Finally you are going a higher potential point. Initially you were at a lower potential point. So change is final minus initial. It's going to be a positive number. If you put minus, it would be a negative number, right? I is a current, positive number. R is a positive number. The change in potential from here to here is positive. That's why I put plus. Whenever you go opposite to the direction of current through a resistor, the change in potential will be positive. You understood the reason? So here it will be plus IR2. That's it. And then you came back here. So this is the total change. This should be 0. So you get EMF is equal to I into R1 plus R2, which is what Ohm's law would have told you. V is equal to IR.
Yeah.
Where R is the total resistance in the circuit and these are in series, so it total resistance is R1 plus R2. Clear? Okay. So in the next class we will do some problems where we apply Kirchoff's voltage loop rule or Kirchoff's second law to solve those problems.